Hi, welcome back. In this video, we're going to introduce the idea of diagonalization of a matrix. We're going to do this by looking at a recent homework problem. So this is going to be problem number 7 from WebAssign 7.1. In problem number 7, we were asked to do 3 things. We were given a 2x2 matrix and told that that was the matrix for a linear transformation from R2 to R2 relative to the standard basis. And we were asked to find the eigenvalues of the matrix, then the eigenvectors of the matrix, and then in the last part, we were asked to find another matrix, A prime, for the same linear transformation, but the matrix was supposed to be relative to the basis B prime consisting of the eigenvectors of the matrix A. So let's review how to do this problem. So first of all, to find the eigenvalues of the 2x2 matrix A, we need to get the characteristic polynomial, which is the determinant of the 2x2 matrix lambda times I2 minus A. So let's set up that determinant. Lambda times I2 minus A is going to be a 2x2 matrix. The first entry is going to be lambda minus 4. The second entry will be 0 minus negative 2. The third entry will be 0 minus 1. The last entry has to be lambda minus 7. Taking the determinant of this, we get lambda minus 4 times lambda minus 7 minus negative 2. If we simplify that, we get a quadratic. Lambda squared minus 11 lambda plus 30. So that's the characteristic polynomial, and we set it equal to 0 and solve. So factoring, I get lambda minus 5 times lambda minus 6. So my two eigenvalues are lambda 1 equals 5 and lambda 2 equals 6. Now to get the eigenvalue or the eigenvectors associated with these two eigenvalues, we have to set up the 2x2 matrix lambda I minus A for each of the lambdas. So the first one is the matrix 5 times I minus A. So the first entry is 5 minus 4, which is 1. The second entry is 0 minus negative 2. Third entry is 0 minus 1. The last entry is 5 minus 7, which is negative 2. And now remember, we're looking for the null space. We're looking for the basis for the null space of this 2x2 matrix. So we use Gauss-Jordan elimination to get the reduced row echelon form, and that turns out to be 1, 2, 0, 0. And so the first row just tells us that x1 equals negative 2x2, and so the vector that we get is negative 2, 1. So that's a basis for the null space of that 2x2 matrix. So it's a basis for that eigenspace associated with lambda 1 equals 5. So let's do it again for lambda 2 equals 6. So the 2x2 matrix, the first entry is 6 minus 4, which is 2. And the last entry is 6 minus 7, which is negative 1. And the reduced row echelon form is just going to be 1, 1, 0, 0. So the first row tells us that x1 equals negative x2. And then the eigenvector associated with that is just 1, negative 1. So that's the second basis. All right, so now in part C, this new basis B prime consists of the two eigenvectors we just found. And notice that does form a basis for R2 because those two eigenvectors are linearly independent. There's no way that one of them is a scalar multiple of the other. So when you have n linearly independent vectors in an n-dimensional vector space, you have a basis. So this is a basis for R2, and because it consists of eigenvectors, it's called an eigenbasis for R2. All right, so I call the two vectors v1 and v2 because to set up A prime, what we need to do is get the 2 by 2 matrix consisting of coordinate vectors relative to B prime of the images of the basis vectors. Remember, the columns are just coordinate vectors relative to the new basis of the images of the basis vectors. So we have to find T of v1 and then get its coordinate vector relative to the basis B prime. And then we have to find T of v2 and get its coordinate vector relative to the basis B prime. All right, so let's find those two images. So T of v1 is going to be, of course, lambda 1 times v1, and lambda 1 was 5, so it's 5 times v1. And now to get the coordinate vector relative to the basis B prime, we find the coefficients in the linear combination of c1 times v1 plus c2 times v2. Well, clearly the coefficients are 5 and 0, so the coordinate vector relative to B prime of T of v1 is the vector 5, 0. And the same thing goes for T of v2. T of v2 is 6 times v2, and the linear combination of that vector, of the two basis vectors, is just 0 times v1 plus 6 times v2. So its coordinate vector relative to that basis is just going to be the vector 0, 6. All right, so those are the two columns of our new matrix A prime. A prime is 5, 0, 0, 6. All right, so notice that this means that A is similar to A prime because they represent the same linear transformation. And this is kind of cool. A is similar to a diagonal matrix, and not only that, the eigenvalues of A are the diagonal entries. And this is going to be our goal in 7.2. So this also means that A prime is equal to P inverse AP for some invertible matrix P. And so we'll be looking at what that matrix P has to be. Let me ask a question. So what is the characteristic polynomial of this new matrix A prime? So I'll give you a minute to find that characteristic polynomial. Okay, to get the characteristic polynomial, you just set up the matrix lambda times I minus A prime and take the determinant. And so you're taking the determinant of lambda minus 5, 0, 0, lambda minus 6, and that's just lambda minus 5 times lambda minus 6. A and A prime have the same characteristic polynomial, so it turns out they have the same eigenvalues. All right, and that brings us to our first theorem in section 7.2. This is theorem 7.4. It just says similar matrices always have the same eigenvalues. So in 7.2, we're going to be looking at matrices that are similar to diagonal matrices. Not all of them are, but we'll be interested in the ones that are. And I'll see you in some later videos.